Let's wait a few minutes.
It's up to you, but whenever you set ready, I will start the recording.
Yeah, let me get what you sent to me because I don't know. Let me see, got it. Let me see. Okay. What happened? Okay, I got it. Now, since there's 2 minutes past 8 o'clock at our time, and let's just start. It'll take me a few minutes to introduce those speakers. So today's talk will consist of 2 talks. One is a theory talk by Kfir Blum. The other will be by experimental talk by Yue-Hang Leung on nuclei and hypernuclei production in relatively heavy collisions. So Dr. Kfir Blum, he is now an associate professor at the Weizmann Institute in Israel. And since 2015, and before he joined Weizmann as a faculty, he spent 4 years as a postdoc at the Institute of Advanced Study at Princeton. And I think before that, if I do not make a mistake, he received a PhD from Weizmann Institute. And then during that time, when he is a faculty of Weizmann Institute, he spent 3 years, 2017 to 2020, on leave as a staff member at the CERN. His research interest mainly in theoretical particle physics beyond the standard model, and also its relation to astrophysics and cosmology. So today he's going to talk about RHIC Beam Energy Scan, talk about hypernuclear production and the coalescence correlations relation. So why don't you start? You have 30 minutes, so I'll give you some warning before the time is up. Thank you. Go ahead.
Thank you very much to the chairman. Yes, maybe the title for my talk is Hypernuclei and Hypernuclear Production and the Coalescence Correlation Relation. I would say in advance, it's a general perspective, and it focuses on one particular problem related to heavy ion collisions that I find fascinating. And maybe striking enough that even an outsider like myself can somehow be magnetized to it. It's a problem they're all very familiar with, I think. So the talk, it will be a theoretical perspective. It will be very general. In particular, it's not in fact making detailed connection to the RHIC program, apart from, as you will see, me repeatedly saying that there are some things that I would love to see in the RHIC program. But then I'm very much looking forward for discussion with experimentalists and theorists on how to do that. And I should add that please, anybody with comments or questions, as far as I'm concerned, are more than welcome to shoot a question during the talk. It's nicer that way for me than just a long monologue. Okay, let's see if I can change slide. Yes. So I've looked at your program of this RHIC program of seminars and discussions, and it is very rich. As of course you know much better than me. It includes many detailed and interesting questions. I am here taking a big step back, and I'm asking just a very basic question, which is the one you're all familiar with. Why does the thermal model work for nuclei? And this is an example. Of course, you see it in all programs, essentially. So at relatively high root S, both at the LHC, like this plot from, like this data here, but also, of course, in the RHIC program. And what this familiar plot is showing is the yields, just dn by dy at central y. for hadrons, starting from mesons and all the way down to very composite nuclei, like helium-4. And so the first part of the sentence I'm making in this question is, why does the thermal model work? I think there is, as far as I'm concerned, there is no question that the thermal fit is working beautifully. What do I mean by that? I mean that, for example, if I go to deuterons and I compare them to helium-3, then, you know, if you just put in at the degeneracy factors times mt to the 3½ with the same temperature times the Boltzmann factor, just the simplest Boltzmann function in front, then you get this prediction 340 for the ratio of the yields of deuterons to the yields of helium-3, which is, as you can see, I just put the lines for this very simple expression for the ratio, and you see there is excellent agreement to within order 1, right? There is room for a factor of 2, maybe discrepancy, but within order 1, there is with over a factor of 340, there is agreement for this trivial expression, and the agreement works for a temperature. There is one parameter in this problem, or in this simple assessment, it's temperature. And this relation works with a parameter temperature of 155, 156 MeV. And the interesting thing for me, or the striking puzzle, is that the same temperature parameter essentially describes the entire thermal fit. So the thermal fit here, I believe, are the blue lines, and the red points are the experimental data. And the same temperature parameter describes this whole range, and this is 9 orders of magnitude. So the first part of the sentence is true. The thermal model works. And the surprising part, obviously, is that it's working for nuclei, for the composite states, very composite states, or made of loosely bound nucleons, with the same temperature parameter as it does for, let's call it fundamental nucleons, protons, for example, and all the way up to pions. Why does this thermal situation works all the way to nucleons, right? That's the puzzle. Why is this a big puzzle? It's a puzzle because if you look at the schematic picture of the evolution of the state produced in heavy ion collisions, then we start from a very plausibly very dense and hot superfluid whatnot state. And there is the temperature of 155 or 156 MeV describes this region that is called chemical freeze out. The name is simply because it describes essentially the ratio of hadrons. But the kinetic temperature, when we actually look at the spectrum, at the PT spectrum of particles, the kinetic degrees of freedom, they are described by a lower temperature, significantly lower temperature, which is what we think of as kinetic freeze out. And the point is that a state like deuterons or helium-3 should interact numerous times. It's not a complicated calculation. It should interact numerous times between the surface of chemical freeze out to the surface of kinetic freeze out. The typical energies of these collisions are larger than the binding energy, certainly in the initial part. And now if I would use the freeze out, the kinetic freeze out temperature in this Boltzmann factor, I will be totally off. Right? So why? So these loosely bound systems cannot be frozen out at the chemical temperature that works for the fundamental hadrons. So why does it work? Right? That's the basic puzzle for me, or a basic puzzle that I find fascinating. And I think at this statement, I attach it at least to Mrówczyński. I apologize if somebody else said it before, but Mrówczyński called it, instead of snowballs in hell, snowballs from hell, which is the essence of the idea of coalescence. And so the idea of coalescence, I'm describing it, but of course there are orders of magnitude bigger experts in the audience than myself. But the idea of coalescence is that you may be able to produce a thermal state that describes the abundance of these fundamental hadrons and mesons. But by the time you reach kinetic freeze out, this is no longer the case for the composite, for the clusters, for the nuclei. Rather than that, the nuclei formed by quantum coalescence at or near the time of or the region of kinetic freeze-out, and they effectively inherit this Boltzmann factor from the constituent nucleons. That's the coalescence in a nutshell. And the literature of this is ancient, as you know. Ulrich Heinz is here as what I think is a seminal paper from more than 20 years ago, where he makes an interesting point about how this system probably works, this idea probably works. That will be relevant to what I will say. But what I did here, I put these shaded regions on the deuterons, the helium-3, and the hypertriton. And what I mean by those are very rough assessment of the prediction of coalescence. This picture that I'm describing here, the prediction of coalescence for the yields of the composite clusters. The bottom line is, and I put very rough, uncertainty estimates that I'll show in more detail later. And so the lesson from this, for me, it's already striking, and Uli made this point early on with early data. Coalescence more or less works. It works to order 1, as you will see. Again, over these 9 orders of magnitude, or many orders of magnitude. So coalescence has a very good fighting chance. I mean, in terms of the observational perspective, it's working, I would say. So how do we understand which of these frameworks we think is the answer to the puzzle? So a point that I think that Uli stressed in this 99 paper was that there is a way to calibrate the predictions of nuclear yields from coalescence using femtoscopic measurements. So basically data from correlation measurements between pairs of final state particles like kaons, pions, and even better protons if you have them, and others. And today there are also P lambda and so on. And so Uli made this point within a particular model, hydrodynamical model of the evolution of this underlying state producing the heavy ion collision. And I think, and so basically this prediction says with the calibration from the femtoscopic measurements, this prediction gave results that are consistent roughly with data. What this plot here is showing is the black line is, okay, first the y-axis is the B3 coalescence parameter for helions, and the x-axis is the HBT radius R in a one-dimensional fit to femtoscopic correlation measurements. And the interesting point is that you can see there are here data, very rough assessment of the data. It's from this paper by Francesca Bellini and myself and Alex and Maximiliano. And this is based on earlier work with postdocs at Weizmann. The point is that on this plot, there are rough assessment of data from many different systems. There are lead initial states at different centralities. There are proton leads, and there are proton-proton. I very much apologize to the RHIC organizer. This is Alice data. It's just my cernophilic history, essentially, or mostly. But I think this must be done also in other programs like the RHIC. And the black line is a coalescence correlation relation. By this I mean it's a coalescence prediction calibrated with no free parameters, just from HBT. Okay, so the theory says, my claim is very related to things that Uli said 20 years ago, but here I think made more general. The claim is HBT measurements up to potentially known quantities that have theory uncertainties, but no free parameters, predict yields. And this black line is what we think the prediction is. And the data, again, is roughly compatible to a factor of 2 or so within many orders of magnitude. So this is a much more detailed prediction, if you want, than this one, just yields, right? These are yields in PP, in PLED, and the model better work here roughly. But the model works much more. It gives much more detailed predictions that I think would be very interesting to test. What's the basic point of this? The basic point is that the x-axis are correlations between free two-particle final states. And the y-axis are yields of loosely bound state. In this particular case, it's a three-body final state. It's the helium-3. I show this here. So the relation is most naturally understood when you talk about something like a deuteron, a two-body final state. Then two-body correlations of free asymptotically free or free propagating particles final state are directly comparable to particles that happen to fall in a bound state. To make this more precise in a few minutes to explain that there is a calculation here. So the basic point is this. In the hadronic collision, be it PP or lead-lead or P-lead, so on, you produce some highly excited initial state. This highly excited initial state, when you probe it with low PT observables, it's not calculable. It is difficult to calculate it. Of course, there are talks here that try to probe various properties and model it and so on, but it's a difficult state to model. I am not even going to try to understand this object deeply theoretically. Of course, it's a fascinating object, but I am not completely sure that we need to know its properties in great detail in order to answer this question of the puzzle, if you want, of the snowballs in hell, right? That is my biggest motivation here. I think we can try to understand something more broadly. And so all I want to do is to attach a density matrix, a two-particle density matrix to this state. What does this mean? It means that if you pluck out at infinity, right, two momentum states or two particles that are flying out of this, then the initial state defines a density matrix. It's reduced. We already integrate out over all other degrees of freedom that are flying out of this fireball, but it produces this state. This state is essentially the square of a matrix element, or half of a matrix element, if you want. And Lednitsky explains it, I find, very, very nicely. And the whole idea of coalescence is that you're going to assume that the same underlying density matrix is the source of particles that end up flying freely in your detector and particles that end up flying into a bound state. Once you assume this, you are essentially done in terms of the predictions of coalescence. So the point is, if I have this density matrix that appears here, I can write an expression. This expression is a quantum field theory expression. It's a bit confusing because it looks like integrals over space-time coordinates x. But of course, these are just Fourier transform of objects that we're used to think of in momentum space sometimes in collider physics. So this density matrix is just the configuration space representation of a matrix element square. That's what it is, describing the initial state, which I don't know much about. Now the psi's are basically two-particle wave functions that describes these states that are flying out of the system. What we are doing, we're taking this initial density matrix and projecting it into some final state that we measure in the detector at infinite distance. And this is this projection and gives you the yield. A very similar operation is, or essentially the same spirit of operation is done where we're talking about two of these particles that end up flying as a bound state. The yield of this bound state looks like a very similar integral. We project, the assumption here is that we can use the same underlying density matrix. It's the same object here and here, but this time to project on a bound state wave function. Okay, we do this often when we discuss the production of composite particles like B mesons, for example, and so on and so forth. In collider physics. So we're doing the same here, we're doing with nuclei. Now, from this discussion, you can go to correlation functions. Correlation functions essentially are the ratio of the two particle yields to, so the, or if you want, the interesting part of correlation function is the ratio of two particle yields to mixed events, two particle distributions that are by definition not interacting. For example, mixed events taking from different from different events in the different states, taking from different events in the collider. And this object is a way that experimentalists often, schematic way that experiments that describe correlation functions. Okay, and now this object depends on P, the total momentum of the two-particle state, and the momentum difference. Now, of course, how people analyze two-particle correlation functions, there is a standard way that people do it. It's HBT, femtoscopy, call it what you want. The bottom line is they're trying to extract some information about this state. And this information is described in terms of some source function. So in some spin state S, we have to sum over the spin states, and we do it anyway. What these measurements are measuring is some object S. This is the two-particle source, effective two-particle source, that is folded with the two-particle wave function. So this two-particle wave function describes final state interactions. That's its goal in life. It includes, for example, Coulomb interactions and nuclear interactions, as far as we can model them. Modeling them is not easy. There are groups like the groups of Laura Fabieti that is working very hard to do this modeling. But this modeling is based on measured, if you want, measured parameterizations of the nuclear interactions, and of course known correlations of the Coulomb interactions. So this is a wave function that we know in principle, and this wave function is non-relativistic because in the center of mass we're interested in objects that are non-relativistic in center of mass, low Q. So this is how correlations are always analyzed. This is what we do, and I should have said that this Bethe-Salpeter wave function, this QFT object, becomes quantum mechanics non-relativistic if you just decompose it into a center of mass, or the total momentum times an internal wave function. So it's this internal wave function that comes in. It comes in this expression. So this is under the hood of what is always done. And I take half a minute to break this particular part a bit more in detail. Most of you are very familiar with this, but it's good to have a general look once. So what are we actually doing when you look at this integral over here? Substituting the internal wave function into the wave function, then what we have, this integral breaks down into a part that it's basically the internal Wigner density of the state. That's this D. It's an integral that's only looking at this non-relativistic two-particle wave function. Just a second, I see there is a hand, and I will get to it in a minute. Times an object that does not know anything about the internal wave function at this point. That's this S tilde. This is some integral of the density matrix of the source rho. Okay, so S tilde is the source, and D is the internal Wigner density, and there is this factorization under the integrals. And S2 is just a certain moment of this source that I'm not going to pretend to be able to compute. In some models, in hydro models, for example, you can compute this object explicitly if you want. These are phenomenological models or theory-inspired phenomenological models. I'm not going to even try to do that. The point is that when we analyze two-particle correlations, we access the object we access. The source is this object. Now, coalescence is the same calculation. The only difference of the coalescence factor is now the ratio of the yield to the product of the yield of separate nuclei, flying to the same total P. I can write it this way. And the point is, when you follow the same calculation, the same assumptions, you are inevitably led to the fact that correlation functions and coalescence are just different integrals of the same underlying source. Okay, so if you find it interesting, or if you accept the way that two-particle correlation functions are analyzed in terms of a way to extract this S2, the two-particle source, then it is inevitable that coalescence should also work in this formalism. Okay, there will be order one uncertainties in the interpretation of both of these objects, at least order one uncertainties. There are assumptions I didn't go into that I'm happy to go into, but basically these are the same objects. Just one folds the source over the bound state wave function, and another folds the source over an FSR final state interacting wave function of these two particles that are flying out. And so there is a clear relation between two-particle correlations and coalescence, and it is essentially model independent in the sense that I don't even care, and I don't pretend to understand how the source comes to be. How is it realized by the initial state? That's a whole area of study that I'm not going into. All I want to understand is this relation between the objects satisfied experimentally, because if it is, we have a very strong confirmation of the coalescence picture. Okay, I think I will go on. Was the question urgent? Maybe the person who asked the question can go ahead. I think I can.
I don't think there's any questions.
All right.
You have 5 minutes to go. Could you finish in 5
I will
minutes?
give it. I can do it.
Thank you.
Thank you for telling me. Okay, so it's the same object. So what to do? What would I like to see for that particular question of the formation mechanism? I would love to see nuclear yields and correlation measurements on the same plot in a way that I will explain, with the same cuts, the same, for example, on rapidity and PT and multiplicity and whatnot. Because I would like to test this relation. If we can test this relation, and it works, we are getting a strong confirmation for coalescence. If it fails, we're getting strong argument against potentially. Back to what I said before, there are order 1 uncertainties in these calculations, but up to order 1 is not so bad. I mean, we are trying to understand the relation that works to orders of magnitude. Our competitor is also working to roughly order 1. If we can do this to order 1, we seem to be able to do this to order 1. Here is an example. So these are B2 and B3. And this is an example of the type of plots that I would love to see done by experimentalists. So this is myself together with a group of experimentalists. But this is a mishmash. We are collecting HBT data from one presentation of the data by the experiment and coalescence from another, and we're trying to make it apples to apples, but it would be lovely to see this coming directly from the experiments at the LHC and the RHIC. And either way, it seems to be working again to a factor of 2, roughly 2 to 3, over orders of magnitude in yield for different species. Alice is making progress on this program. This is an example that I didn't have much time to go into, and it would be fantastic to see a similar program at RHIC. I can go back to comments on what I think is good and maybe can be improved in this plot, but this is a fantastic direction because in this plot, they're really trying to put the yields and the HBT on the same with the same cuts and so on. Now, hypernuclei, of course, I've been crying about order 1 uncertainties in the calculations, theoretical uncertainties. What we really want is a system that tests the coalescence idea with effects of order of factor of 10, or an order of magnitude, and hypertriton is an excellent example because it's huge. The quantum coalescence factor that Uli defined, that should basically suppress the production efficiency of coalescence for a very large state or loosely bound state. It should be at the level of factor of 10 for small initial states. Data that we have already for this from Alice at this point are mostly for large initial states. So this is lead-lead. Hypertriton mean lead-lead looks very good for the coalescence model, and it was on my plot of the yields. That I don't see any problem there. That's here. Now there are developments at this point from Alice with smaller system, lead protons. This is an example. At the first glance, I was happy about this plot because it seems to favor, if you look at it from the right angle, it seems to favor coalescence. At this point, I'm not completely sure how to take it. The S3 variable is somewhere in between the thermal model and the coalescence. One comment or 2 comments I wanted to make about this presentation that I would like to see improved in the heavy ion program. First, the theoretical interpretation in this plot is troubling. There is no such thing as 3-body coalescence that is presented here by the experimental collaboration. It simply doesn't exist. There is no such calculation. It does not exist. I don't know what they mean by that. 2-body coalescence is an effective outcome from the coalescence calculation. So this line is the correct one, effectively. This one simply doesn't exist. It's not a prediction. That's one. Second point, the x-axis here is not HBT. It's multiplicity. And these may not be the same. You have to be careful. So this is an extrapolation to some extent of data. Oops, sorry. And they may not be the same. You have to be a bit careful. But this is a good step in the right direction. The experiments have data for PP, and here we are really waiting. So PP should come out. We should see the separation factor clearly. So I think this is extremely promising. The collaboration that manages to measure hypertriton S3 or coalescence factor with PP initial state or small system initial state I think can make a breakthrough. Okay, so I'm done. My summary is 3 very short slides. First, to my opinion, coalescence is irreducible in the same framework in which you analyze HBT. If you accept the interpretation of HBT, then coalescence is inevitable. We don't know how much, or it's not clear how efficient it is, or maybe there are other channels, but it's there. That's one. Second, it roughly works. It actually makes detailed prediction if you calibrate to HBT. They roughly work. It would be lovely to see this by experimentalists directly. Hypertriton, as you know, is golden because it's big. It's working okay. Coalescence is working in lead-lead. I don't know in P-lead. I think it's open for debate. And what we really want to see is a very small system. Okay, thanks very much.
Thank you, Kfir, for your nice talk to emphasize the relation between correlation and the coalescence. So now, unless there's urgent questions, I'd like to postpone the discussion after the second talk. And that's one question in chat. Let me see. Okay, Kaijia just asked short questions, then we will continue. Go ahead, Kaijia.
Oh, yes, thank you. Hi, thank you very much for the nice talk. Yeah, as for your comment on the 3-body coalescence for hypertriton, yeah, I want to just want to mention that in the 3-body coalescence calculation, it was assumed that the neutron, proton, lambda are nearly equally distributed inside the hypertriton wave function. So of course, this assumption is not a good assumption, and the neutron and the proton inside the hypertriton is almost a neutron, yeah, right?
Exactly. So let me just make a statement on this. So absolutely, I completely agree. The one little point is that there really is no such thing as 2-body versus 3-body coalescence. This is a 3-body final state. It has a 3-body wave function. If you plug the wrong wave function there and you know it's wrong, you're gonna get a wrong answer. If you plug the right one, you're gonna get a better answer. We should use the wave function that more or less works. Either way, the calculation doesn't know about 3 versus 2-body. It spits out a result that is effectively similar in structure to 2-body because of the structure of the wave function. But so, yes, but I understand what you're saying.
Okay, that sounds really interesting questions that we can continue to discuss after the second talk. So thanks again, Kfir. So let's try to go to the second talk by Yue-Hang Leung. And he'll talk about the, Kfir, can you leave the screen so that Yue-Hang Leung to share the screen?
Yes, I think it's okay.
Okay, it's there, great. So let me introduce briefly Yue-Hang Leung. Yue-Hang Leung is now a postdoc researcher at the University of Heidelberg and associated with STAR collaboration and CBM collaboration. And before that, he was a postdoc at Berkeley for a short period of time. And that's when he switched from Phoenix collaboration to STAR collaboration. The reason because his thesis was with Axel Dries at Stony Brook, working on Phoenix physics. So now he's working extensively on the beam energy scan and also light nuclei productions in heavy-ion collisions. So today here, we have an overview or summary of the present status of light and hypernuclear production in heavy-ion collision and its future prospects. Please take over.
Yeah, thank you very much for the nice introduction. Actually, can you see the screen?
Yes, we do.
We see
Okay.
double screen. Yeah.
Oh, you have double screen.
Yeah.
How about this?
Yeah, now works.
Okay, thanks. Okay, so hello everyone. So thank you for the organizers for giving me this opportunity to talk about the experimental aspects of light nuclei and hypernuclei production. So in terms of the RHIC Beam Energy Scan, I think one of the main motivations of the Beam Energy Scan is to learn about the QCD phase diagram in order, and in particular, search for the critical point and the onset of the confinement. So I think one particular question that is quite important is whether light nuclei production and hypernuclei production in heavy ion collisions, can it tell us something about the QCD phase diagram? And indeed, it has been suggested in the literature that certain particle ratios formed by light nuclei or hypernuclei could be sensitive to neutron density fluctuations or baryon-strangeness correlations, which can be used to probe the QCD phase transition or the critical point. Another, I think, important question is whether we can learn something about the hyperon-nucleon interaction from hypernuclei production. And this is, I think, particularly interesting because, as we know, recently it has been observed that neutron stars with rather large masses exist, and it's still an ongoing puzzle how such large masses, large mass neutron stars can exist if there are hyperons in their interiors, which supposedly would soften the equation of state. So I think it's still an open question how we can learn about the hyperon-nucleon interaction from hypernuclei production in heavy ion collisions in order to provide insights to solve this so-called hyperon puzzle. But before that, of course, it is also maybe even more important to first understand how these objects are formed in heavy ion collisions. So I think this Kfir has already talked about it in great detail. So I won't talk about these thermal model and coalescence models again. I'll just mention here that besides these two models, there are also these other processes that could affect nuclei production heavy ion collisions. For example, these hadronic interactions that are listed here. So one thing to note is that these reactions, they go both ways. They can both create nuclei or destroy nuclei. Another, I think, also important process that cannot be neglected, particularly in lower energy collisions, are from fragmentation. And basically, these spectators could fragment into smaller, stable nuclei. And this is particularly important in low energy collisions because the beam rapidity becomes closer to the mid rapidity. And one thing probably to note is that there are also suggestions from the theory community that if these spectators, they capture hyperons, these excited hyperclusters could also fragment into hypernuclei. Okay, so this is sort of the roadmap of this talk. I'll mainly be focusing on the production yield measurements from the experiment, but I'll also talk a little bit about the flow, the correlations, and the cumulants. And although I know that the topic is production of nuclei, I'll also briefly talk a little bit about some measurements on hypernuclear properties, because I think clearly they are also relevant for their production heavy ion collisions, and also there are implications to the equation of states at high baryon density, which is also an important motivation for the Beam Energy Scan program at RHIC. Okay, so of course I'll mainly be focusing on the STAR Beam Energy Scan results. As we know, the STAR Beam Energy Scan 2 has recently concluded. And one particularly interesting feature of the Beam Energy Scan 2 is that it can reach energies down to 3 GeV, which is because STAR is able to run using the fixed target mode. And this allows us to actually cover a very wide range in energy, 3 to 200 GeV, which corresponds to 20 to 700 50 MeV in the baryon potential. And I'll also be mentioning some Alice and Harder's results that are also relevant for this topical discussion. Okay, so let's first look at the production yields. What is shown here on the left-hand side is a recent published result from the Star Beam Energy Scan 1. And what is plotted here, the blue points, they are the neutron over proton ratio as a function of the beam energy. And you can see that when compared to thermal model predictions, which is indicated using this black solid line here, they're actually quite, they follow this predictions quite closely. On the other hand, if you look at the red points, which are triton to proton ratio, we see that it actually deviates from the thermal model predictions between 7.7 to 200 GeV by a close to factor of 2. On the other hand, it is consistent with the Alice measurement at 2.76 TeV, considering the uncertainties. And one possible explanation from the literature is perhaps that the triton could be affected by the reactions, hadronic reactions in the rescattering phase, where these reactions could preferentially disintegrate the tritons compared to generating them. So that's one of the explanations. And using these proton, neutron, and triton yields, we can construct this compound ratio, which is shown here. And this is plotted as a function of the charge particle multiplicity. It's because charge particle multiplicity is a sort of a proxy for the volume. And we see that the compound ratio follows scales with the charge particle multiplicity reasonably well from 7.7 to 200 GeV. And here we also compare to various model calculations. So what is shown here in using the dashed lines here are thermal fist model calculations, which is a thermal model which can optionally include excited nuclei states. And we see that at these higher multiplicity regions, it deviates quite strongly from the data. As for the coalescence model calculations, we see that the green dashed line and the blue dashed lines here, which represents hadronic transport models interfaced with the coalescence after Bernoulli, they can roughly reproduce this trend as well. So it seems that the data favors a coalescence prescription as compared to the thermal model calculation.
This thermal model has mu equals 0, right?
That's right. So
which is completely wrong.
Well, I mean, it doesn't deviate too strongly at high energies.
Well,
right?
At the right, no, but at the left, if mu is 700 MeV, then it orders of magnitude wrong, right?
Mm-hmm. I mean, I agree with what you said, of course. This only applies to the very highest energies. But
yeah, I think Edward has a good point. So let's discuss that after your talk.
Yeah. Okay. Yeah. I agree with this comment. Okay, so one of the main reasons why we want to study this ratio is because it has been proposed that in the vicinity of the critical point, the density fluctuations become larger. And if indeed the light nuclei they are formed via the coalescence prescription, then we would also expect light nuclei ratios to have fluctuations. And indeed, this ratio has been proposed to be directly related to neutron density fluctuations. And what is shown on the left-hand side, this is the compound ratio as a function of the beam energy in central collisions. And you can see that there's seemingly a small enhancement around 19.6 and 27 GeV, whereas it's not that evident in the peripheral collisions that's shown on the right-hand side. And so one, I think, important thing to note here also is are these blue dashed line. So in order to obtain these ratios, extrapolations to zero momentum is applied, and that's basically because that only covers limited PT acceptance. And if we only look at the acceptance that's covered by the experiment, you can see that these enhancements, that the ratio in this rather constrained momentum range, the enhancements becomes less significant. And I think clearly more studies, for example, using the Beam Energy Scan 2 data with larger acceptance and higher statistics would be useful to draw a stronger conclusion. Okay, so these are some results from the Beam Energy Scan 1 program. We can also look at the Beam Energy Scan 2 program, and what is shown here is the 3 GeV data that's collected in 2018. If you look at the left-hand side of the corner plots, we can see observe fragments up to A=6. And yeah, so the nice thing about this data set is that there's actually quite nice mid-rapidity coverage for most particles. And as you can see here, the proton, neutron, triton, helium-3, and helium-4 rapidity densities are shown on the lower left-hand corner. And the red dashed lines, which represents the SMASH hadronic transport model interfaced with coalescence. You can see that it described the data reasonably well at mid-rapidity. And one thing that I would like to point out here first is that if we look at helium-4, clearly in the more peripheral collisions, the yields rise towards the beam rapidity or the target rapidity. So this could be coming from the fragmentation of light nuclei. Besides the light nuclei, copious amounts of hypernuclei are also observed in the data as shown on the right-hand side upper corner. So these hypernuclei, they are reconstructed by using the weak decay channels. And similarly, we can obtain the rapidity densities, which are shown on the left-hand side here. The gray points are hypertriton and the red points are hypernuclei. And I think similar to what we've seen for light nuclei, there's also rapidity dependence here, centrality dependence in the rapidity trends, in particular for H4 lambda. We clearly see that the yields rises towards the beam rapidity, which some of it could be coming from fragmentation of strange spectator matter. So besides 3 GeV, we've also obtained the hypertriton yield at 19.6 and 27 GeV, which is shown on the right-hand side. This is a plot of the hypernuclei yield as a function of the beam energy. And the red and the blue dashed curves represent thermal model from Heidelberg GSI and the thermal fist model. And you can see that they describe hypertriton yield at 2.76 TeV quite well. The yield that the trend is in general also quite well reproduced, although I think it's worth pointing out that at 19.6 and 27 GeV, these calculations from the thermal model are also overestimate the yield. So I think this feature is quite similar to what has been observed for the tritons. So in order to compare the hypernuclei to light nuclei yields more quantitatively, we can also look at this as A factors, which are commonly known as the strangeness population factor. It's basically the hypernuclei yield divided by the light nuclei yield, and then additionally also divided by the lambda over proton yield to account for the difference between the densities of the lambda and the proton. So this ratio can be determined differentially in momentum, rapidity, and centrality, and that's what's shown here on the right-hand side in the 3 GeV collisions. So we can see that, so what is shown here, the magenta points, they represent A=4, A=4, and the blue points represents A=3. And what you see here is that the yield, the ratios, they do not depend strongly on rapidity, momentum, or the centrality. They're basically almost constant. And so this, I think, implies that the mechanics behind the formation of hypernuclei and nuclei are quite similar. Another thing that's worth pointing out is that the A = 4 population factor actually is significantly larger than that of A = 3. And one explanation for this enhanced value of A = 4 comes from the fact that we know that the excited states of H4 lambda exist, and it has a spin 1, which corresponds to a spin degeneracy of 3. And if they are equally populated, if all states are equally populated compared to the ground state, and we can expect a factor of 4 enhancement in the H4 lambda yield, because these excited states, they decay via gamma transition to the ground state. So this is an explanation of how of why this A = 4 ratio is higher compared to the A = 3. But of course, there could be also other factors that could affect these ratios. So this strangeness population factor was originally proposed because it could be a signature on the onset of the confinement. And in the original proposal, this blue dashed line here from AFPT calculations, you see that in the presence of the confined matter, this S3 ratio actually rises quite rapidly with the beam energy, whereas in hadronic matter, it's quite flat, rather constant, and sits at lower value. So if we look at the S3 ratio as a function of the beam energy, that could potentially help us search for the onset of the confinement. Now we look at the data, which is shown using the red and black colored points. I think that seems to be a small hint of an increasing trend. Of course, more data would be needed to confirm this, but one thing to also point out is that actually recently there are also other suggestions from the literature that could give rise to potentially rising trends. For example, the coalescence model believes that at the lowest energies, the hypertriton yields could actually be suppressed because the radii of these hypertritons are quite large compared to the source sizes. And as you can see using the orange, indicated using this orange band here, this model also gives an increasing trend. Another possible mechanism which could affect the S3 dependence on energy is suggested by these thermal models. So these thermal-fist models, they include nuclei breakup from unstable nuclei. It assumes that all these nuclei, they are equally populated regardless of their binding energy. And particularly at lower energies, because the baryon density is high and the suppression factor is lower. The breakup of these unstable states could lead to rather significant enhancements in the helium-3 yield, which would then, of course, suppress the S3. Okay, so I think there are clearly a lot of work to be done in order to resolve these, to clarify this situation, more differential measurements, possibly measurements of unstable nuclei as well. So I won't go into detail on this slide because Kfir already mentioned this measurement, and I think that the conclusion is that it seems that these measurements of the hypertriton in the small systems favor the coalescence procedure. So as I mentioned earlier, the hyperon-nucleon interaction is also a very important ingredient in our understanding of the nuclear equation of states. And one of the most direct observables in order to constrain the hyperon-nucleon interaction is the measurement of hypernuclei binding energies. And indeed, if you look at the left-hand side, this is the red one is a recent measurement of the binding energy from ALICE. Right? It's actually the most precise measurement so far. And I think it is expected this will give stronger constraints on the hyperon-nucleon interaction. As for star, star has also recently measured the H4 lambda and helium-4 lambda binding energies. And, the uncertainties are still quite large, as you can see, but I think, expect them to be reduced once we have the full data set. And this is particularly interesting also because H4 lambda and helium-4 lambda, they're mirror hypernuclei. They only differ by replacing a proton with a neutron. And this is one of the ways for us to investigate the isospin dependence of the hyperon-nucleon interaction, which is up to now not very well understood. Another, I think, also interesting measurement coming from the hypernuclear lifetime. So due to time, I won't go into details here, but just to say that the uncertainties from the older emulsion experiments are typically quite large, and with the advent of hypernuclei measurements from heavy ion collisions, such as star, ALICE, others, we actually see the uncertainties shrinking, I think, quite rapidly. And I think in the near future, we would have also very precise, even more precise measurements, which could help us further understand the structure of these hypernuclei. Okay, so in the next part of the talk, I'll talk a little bit about some other observables, namely the collective flow, the femtoscopic correlations, and also briefly the cumulant ratios. So what is shown here, this is a recent published measurement from STAR of the hypernuclei and light nuclei directed flow. And this is the directed flow, slope of the directed flow plotted as a function of mass for light nuclei, shown using the gold markers, and hypernuclei shown using the red markers. And I think you can see that for both cases, they follow roughly a mass number scaling, which is expected from coalescence, because in the coalescence procedure, the hypernuclei or light nuclei, they could inherit the flow from their constituent nucleons or hyperons. And what is also shown here are some model calculations, which come from hadronic transport models interfaced with coalescence afterburners. And you can see that they also approximately describe the data. So another interesting observable that we can look at are these femtoscopic correlations. So I think Kfir already explained what these correlation functions are. They depend on the emission source and the two-particle wave function. And what is shown on the right-hand side, this is actually the correlation function between a proton and a neutron from ALICE, proton-proton 13 TeV collisions. And what is shown here, as you can see, is that this K-star variable, the relative momentum, actually shows a depletion at the lowest K-star values for the proton-neutron correlation function. So how does one interpret this? Well, in this particular plot, as you can see, they're compared to various model calculations here. And if you look at the red line here, this red model calculation makes two assumptions. Number one is that all particles, including the neutrons and the protons, they basically have a common empty scaling. So this assumption assumes that all the particles, including the neutrons, they arise from the exact same source. And second one is that the interacting potential between the proton and neutron is assumed to, the neutron is assumed to be point-like and is constrained by previous scattering measurements. And you can see that these two assumptions give rise to actually pure enhancement at low K-star, which is not very compatible with the data. And one way to interpret this is that, as you can see, they have gradually increased the source size. They've increased the distance between the protons and the neutrons. And it seems that at around 3 femtometers of the source size, this model can roughly describe the data. So one possible interpretation is that these neutrons are formed at a later stage compared to the other particles. Similar measurements have also been done at SR, this time at reach EV, its lowest energies. And the first row here shows the proton-neutron correlation functions in different centrality intervals. And you can see, similar to what Alice has observed, also a depletion at low K star can be seen. Besides the proton-neutron correlation functions, the neutron-neutron correlation functions are also plotted here in the bottom row, and these are compared to actually two scenarios. Number one, the blue line represents the SPASH hadronic transport model interfaced with the correlation after burner, and the red line here is the same hadronic transport model, but this time first interfaced with the coalescence after burner to form the neutrons from the protons and neutrons, and subsequently interfaced with the correlation after burner. And it seems that with the inclusion of the coalescence after burner, the data can be more or less described. So finally, I would like to spend the last few minutes to talk about these number correlations between and cumulant ratio. So besides the correlation function between the proton and neutron, we can actually also measure the correlation between the number of protons and neutrons observed in each event. And so basically, this is characterized by this Pearson correlation coefficient. I won't go into the exact details here, but I think it suffices to say a positive correlation coefficient would tell us that the protons and the neutron number would be positively correlated, and a negative value would tell us that they are oppositely correlated. And you can see that the Alice measurement of antiprotons and antineutrons in lead-lead collisions at 5.02 TeV indicates that this coefficient is negative. So it actually tells us that their production are anti-correlated with each other. And these are compared to various model calculations. It is shown here that thermal model calculations using the canonical ensemble with a particular volume where baryon conservation is required can describe the data. On the other hand, it seems that the coalescence models actually don't quite describe the data. So we can see that there are two different models here. One assumes that the proton number and the neutron number are fully correlated, and one assumes that they are independent, and neither of them seems to describe the data. But we can also look at the star data as well. And the same coefficient is plotted on the right-hand side, bottom corner. This is time as a function of the beam energy from 7.7 to 200 G. So first of all, we observe that all of them are negative. So I think this is, again, indicates that the proton and neutron production are anti-correlated with each other. It's also compared to the same model. The blue dashed line represents the simple coalescence model. However, I think one thing to note here is that this particular model actually neglects the phase space information. And if one uses a more realistic transport model, such as ULQMD, and subsequently interface with the coalescence after burner, it seems that the data can be more reasonably described by this coalescence prescription. And indeed, if we look at the other cumulant ratios in the other panels, this coalescence procedure also approximately describes these cumulant ratios of the neutron. Okay, so this brings me to my summary. I think we've looked at a rather wide range of light nuclei observables. I think in general, the coalescence model is doing a good job, but of course, perhaps more details in the transport or the coalescence procedure may require more study. And thermal model, on the other hand, it is also actually quite compatible with the neutron observables, but I think the triton yield and the hypertriton yield, there is some tension there. And just as a last note, we are only showing a very small portion of the star beam energy scan today. I think there's still a lot that can be done with a larger acceptance and higher precision and so on. So please stay tuned. And maybe just one last slide, just to say that I think one of the very exciting prospects in the near future comes from double lambda hypernuclei. This is because, as I mentioned in the very beginning, the hyperon-nucleon and the hyperon interaction, these are not well understood interactions. And in order to give important input to solve the hyperon puzzle, these double lambda hypernuclei, which are rarely observed in history, would also give a good constraint. And we await, I think, these experiments that are listed here, including CBM and A60 plus and JPAC heavy, and these have the highest interaction rates, which could give us a chance to observe these rare hypernuclei. Okay, so this is all I have for today, and let me know your suggestions and questions.
No, thank you, Yue-Hang Leung, for the very nice extensive review of like nuclei and hypernuclear productions. I realize your name's not Huang, it's Han, H-A-N-G, the middle name. Right?
Yeah, that's right.
I think it was printed incorrectly in the announcement.
Mm-hmm.
Sorry about that. Now,
That's
before
fine.
we start, let people to raise questions. There are 2 questions in chats. One is by Peter von Munzinger. Unfortunately, he left this meeting for another talk. He asked the following questions. If you can look at the chat. While yields for deuteron and helium-3 are relatively easy to measure, tritons are difficult to measure because of its magnetic rigidity. So I would strongly argue that the star should also measure helium-3 to see how consistent the data are. Do you agree with this statement?
Yeah, I fully agree. I think this is already in progress, and we can see some results soon.
So then the next question is raised by Kaija. Kaija, can you ask a question by yourself?
Oh, yes. First, thank you very much for a very nice talk. Yeah, for the measurements of lambda suppression energy, the B lambda, the value of B lambda, yeah, I see that the value from star collaboration is much larger than that from the latest the latest ALICE measurements. Do you have any explanations? What might such difference?
I mean, my explanation would be that the uncertainties are quite large here. So I think within 2 sigma, they are still consistent. So that would be my interpretation.
Do you have plans to increase to decrease the uncertainty from star?
Yes. I think as we maybe you've seen that we have quite high significance in the lower energies, and this is I think planned for the future. But maybe for this presentation we don't have this result yet.
Okay, thank you very much. Thank you.
We don't hear you.
Edwards, go ahead, ask your question.
Okay, I want to make a general comment. So there are 2 possible mechanisms. One mechanism is what is discussed here, that 2 or 3 or 4 nucleons which make a nuclei actually meet well after the collision. They just coalesce from different places by chance. And that is what Coalescence model does. If that is true, any correlation to phase transition and TC, critical temperature, chemical freeze out is just coincidence, because it all depends on size of the system, not on the temperature it has in the middle of evolution. There is another view, yes, and the other view is that at temperature TC, some cluster is created, and that cluster then developed and make nuclei at the end. Now, which one is happening? So I want to remind that we had a series of studies of that, and find out that yes, two nucleons cannot be held together at critical temperature, but 4 can. So if you have a cluster of 4 nucleons, the mutual attraction is enough to hold it together at TC. And then this cluster can survive and expand and make multiple states of helium-4 and other 4 systems, and then contribute significantly to production not only of helium-4 but tritium-2 at these RHIC energies. Of course, it depends on chemical potential very much, but at least half of tritium come from the decay of excited states of helium-4. There are about 50 states close to 0 in helium-4, which need to be included in the statistical model, and there is a dynamical explanation how it goes. So in other words, there could be 2 sources, I'm saying. One source is that by chance 2 or 3 or 4 nucleons meet way after collision by coalescence, from going from distant points together. The opposite point of view that they were together from the beginning and they form a cluster at TC, and then part of it survive in different forms. So,
Okay. Yeah, we got a picture, Edward. So what
Yes.
Edward tried to
yeah,
suggest
I
to
see
you,
that all of
add
this is
another-
completely forgotten.
add another panel in your introductory talk about Edward's mechanism for cluster production.
I
Okay?
just need to remind you that it still was done. Yes, you guys forgot it completely.
Yeah, it's pity. He's also from Stony Brook, but he
Yeah, so
they just add another one in the future. Anyway, so that's another hand raised by Kfir. Could you comment whatever question or comment you may have?
Yes, thanks. I have a question to the experimentalist, but also maybe about maybe to Edward as well. So the idea that just the helium-4 is bound strongly enough to survive is very interesting, and I was not aware of it. That's just my ignorance, so thank you. But do you suggest that this also contributes to objects such as the deuteron or say hypertriton?
it contributes to tritons and neutrons, not at LHC, of course, but when mu is larger. So at 3 GeV, definitely. Yes.
Okay. Yes. So okay. So yeah, at large mu, I guess the life can be a bit more complicated. Thanks. So my question to the experimentalist, and that's actually about the beam energy scan. So you showed the plot quite in the beginning of the D/P ratio as a function of root S. Maybe you can go back to that.
Yeah.
It is which is decreasing very fast. So does this exist also for antiparticles or for some range of energies or not so much?
Antiparticles. You
Yes.
mean anti-neutron to anti-proton?
Yes.
I would expect the anti-neutron yield to decrease quite quickly. So I don't think it. I mean,
You mean
I would think.
at low root S?
Yeah, at low root, that's exactly.
Because
Sure,
mu
but so
works the other way.
I'm sorry?
Mu will work the other way and suppress it instead of
Yeah.
right. Yes.
And so what I'm saying, the D/P, I mean, I would be happier to see a B2 plot, for example, but at least at the higher energies of a few tens of GeV up to hundreds of GeV, and then can be connected right to TeV with Alice, you have a change of about an order of magnitude, right? From roughly 10 GeV. In Triton, you have more than an order of magnitude from TeV to 10 GeV. You have a good 1 or 2 orders of magnitude. If there is a similar trend, at least at relativistic root S, highly relativistic, if there is a similar trend in RT particles, then it would be extremely interesting, for my opinion, to see 2 particle correlations also as a, you know, the effective radius is a function of collision energy, to see if this, because this is a large effect, does coalescence really address it or not.
Well, let me, it's measured. Anti-proton correlation was measured by star.
As a function of root S?
I don't know, it's maybe in one energy or not, I don't know, but it was measured one time. Am I right? I think I remember it's published in Nature somewhere, long time ago.
And what about the, I see. And what about the, well, we can convert then, I mean, we can calculate coalescence factors easily. But the antiparticle coalescence factors or yields, this is also
Sure.
available.
Then Ed was right? The D bar P ratio will go down as you go to lower squared S.
But if you have a root S effect that gets to an order of magnitude, as you go from tens of GeV, below tens of GeV, I don't know what to do, but as you go from 10 of GeV to TeV, that would be very interesting. I would love to discuss it if anybody's interested in business to try to see if coalescence agrees or not.
Let me see, I do not see another hand raised. Any other questions from the audience? Actually, I have a couple questions. Everybody can interrupt me. I have a couple questions. When you look at deuteron correlation, deuteron proton correlation, you remember when you measure that one. In the correlation, HPT correlation, you need a final state interaction as mentioned by Kfir. What do they include in those DD potential between two deuteron in calculate the correlation function in SMASH?
Yeah, I think they are constrained by scattering experiments, but maybe someone.
Oh, they have scattering experiment. Okay, they're just
maybe
curious.
someone in the
I didn't
chat
follow
can
this.
comment on this.
Similarly, for proton deuteron, you also the correlation. You also need the proton deuteron potential.
That's right.
To get
Yeah.
it right.
Yeah. So I
So
believe.
that's right.
Yeah.
So another question I have for you: can you go back to that anti-proton, anti-deuteron correlation, that thermal model versus coalescence model? Just
Thermal
remind
model.
you, in the last few slides.
Last few slides. Oh, this one.
The correlation. Yeah, this one. Yeah, this one. Proton deuteron number correlations. Just remind you, Kaijia wrote a paper just recently published in Fixed View Letters using AMPT model to calculate plus coalescence. And maybe Kaijia, you want to say by yourself?
Oh yeah, yes. It's not a physics zero letter. It's a physics letter B. Yeah.
Oh, okay.
Yeah. We use the coalescence calculation with the implementation of baryon number conservation. So we can explain the lective correlation between anti-proton and anti-deuteron. And the coalescence calculation, yeah, as shown in this slide, which overestimates the data, is because maybe their treatment on the baryon number conservation is not very good. Yeah.
Okay. Yeah, point taken.
So the message is sorry about this. I have somebody working on AC system in my house and making noise. So my comments is what Kaijia discovers those hybrid model of hydro plus URQMD, for example, normally during statistical hadronization, Cooper-Frye, they do not incorporate the baryon number conservation. That is important to understand the proton-deuteron number correlation if one wants to use those hybrid model to study this quantity. Any other questions? Let me see anybody's hand. Nobody's hand. There, anybody comment or questions on first talk by Kfir on the relation between coalescence and particle-particle correlation?
There is a comment in the chat from.
Yes.
I mean,
Ben, go ahead.
It was actually not a real comment. It was mainly connected to what Kfir asked. If there is data from star beam energy scan on anti-neutrons. Actually, it's referenced in the plot I sent. That was, could also have just sent it to Kfir, but I thought perhaps it's also interesting for others.
No, thanks very much, Benjamin. But I noticed also there is just a plot there of
Yes,
direct there is B2 and B3 as a function of root S, and there is not significant dependence. So I think that's more or less, it's still true. If the correlations are significant and we don't see significant effect in the coalescence factors, then we're also in trouble. But if you want, there is a prediction for two particle correlation as a function of root S, that there isn't a huge change when you go from tens of GeV root S to a TeV.
Yes.
Okay, thanks, Ben, for the information. Maybe I'll ask a question again. I remember Kfir, he commented there's no three-body correlation. Could you elaborate it again? Why there's no three-body correlation?
Yes, thank you. It's just that okay, I know how to do this calculation in one way, right? Which is to take a three-body wave function for which we have some theoretical knowledge, similar to what we have in particle correlations, right? Like you asked, where do they take whatever the effective field theory, the nuclear interactions from? Similar from charge radius measurement, etc. We have some model, or from chi-EFT, we have some model for the wave function. So you can take some three-body wave function and you can project it on the source that is measured from two particle correlations. That's the only thing I know how to do, right? If you measure a final state, which is a hypertriton or any other nucleus, that's the wave function you need to project the source onto. There is no even discussion of three-body, two-body. There is this calculation. The source doesn't know, there is no time, for example, in this calculation. There is no place where you form the thing. There is just the source and there is the wave function. So there is one calculation I know how to do. Now, this wave, like we discussed, this wave function for hypertriton, from the calculations and from measurements, we know the lambda is very loose, is very separated from the kind of neutron component. And so if you plug this wave function into the calculation, you get an answer that has the form of a two-body, of what you would get for a neutron formation, for example, just with a different size. But that's an effective answer. There is no situation in which you get the answer of a three-body.
Can I disagree with you? Can I disagree with you?
Okay.
Yeah, I don't know. In your paper, you cite my paper with Zheng Zhang, fixed letter B with the paper about hypertriton production in coalescence model. In that paper, we use the three-body wave function from some Japanese Nomura, and then we parameterize that wave function into many, many Gaussians, right? So then we do the coalescence. We use the source from I forgot which source he got, probably from some blast wave model source. Then he projected the source into that three-body wave function to get the production of hypertriton. That's fixed letter B paper. So I think I think it's possible to do if one knows the three-body wave function for hypertriton or for triton or for helium-3 or even for alpha particle if we know the four-body wave functions.
I see. I take your point. I totally agree. If the wave function, if you want, our best guess for the wave function was from the calculation of Hammer matched to earlier calculations and to some measurements. If this ansatz for the wave function is wrong and the wave function is scattered all over the place in reality.
Oh yes, they do. That wave function for the nucleon, the size about 2 Fermi, 1 or 2 Fermi. For lambda, the size almost 10 Fermi. So lambda really sticking out. So it's very, very, so that's any three-body wave function really describe the lambda binding energy and very well. Because there are a group of people in Japan, they use effective nucleon hyperon interaction, like mentioned by our second speaker. That's important to know the hyperon-nucleon interaction. They solve those problems by diagonalizing some model space, right? Once you know the interaction, you construct some model space, you diagonalize. Then you can get a three-body wave function. So that's a group of people in Japan. They're experts on that kind of calculations. Not really three-body calculation. That's diagonalization of the three-body Hamiltonian with the nucleon hyperon-nucleon interaction. That's the free space nucleon hyperon interactions, and they diagonalize in some basis. And
but, right, but maybe there is something I'm not understanding. So the outcome of this calculation, which I will never pretend to be able to do, okay? But
sure, you cannot do it, but people can
outcome,
do it.
right? Okay, but the outcome is a three-body wave function. Do I understand correctly? The outcome
That's
is a
right.
three-body, and the statement is that the structure of this three-body wave function is totally different from that.
What Kaija mentioned, you just
Right.
Yeah.
So if we got the wave function totally wrong, we're totally off. That's absolutely.
right. But that wave function is probably correct
Why-
because
Why should it be
this-
wrong?
yeah, I mean, not 100% right. Because we know it's very difficult to
agree.
get 100% description of nature, right? Especially for strong interacting system. But they do get that hammer shape. They have a neutron, in hypertriton, then you have a lambda sticking way out. So that hammer shape.
With that shape, you should find out an effective answer that is more or less what people call. Well, the paper I was quoting, I was referring to that bothers me, the two-body versus three-body. They're just using.
Well, that one's incorrect. They have some three-body just
Right.
uniform.
There is not.
That's not realistic. Agree.
This is simply not a calculation. So
Okay, agree.
in a coalescence correlation, I find with the hammer kind of shape of wave function, I think you would end up with something that looks like the two-body, but I could be wrong. I completely take your point. Thank you.
Yeah, it's look like the neutron plus a lambda. So any other questions and comments? Seems nobody raised his hands, and also those questions raised in the chat box.
Maybe I have one more. Can I ask something very small?
Oh, please go ahead.
Yes, so my
Kfir.
experimentalist colleague was brave enough to show the Alice PP result for hypertriton, which I myself would love to show, but I talked to my Alice friends and they kind of, they were not very happy. So I wonder if anybody knows why are they not happy, and is there a measurement that is coming out?
Maybe Ben can comment on that.
When did you talk to them? Was it recently? Because this is the preliminary value and it will be in the paper the same value.
It was today, but maybe I talked to a super overcautious Alice. I see. Okay, because the PP result is striking, I would say, in favor of coalescence, and I see. So I shouldn't listen next time to my friends talking about.
Secretly tell me who it was. Because
You can guess. Find the super very cautious one among them, and you got it right.
Okay, but actually also he should, well, it doesn't matter. Yeah, so asking me, I say it's okay. And there will be another point in the paper. Actually, if the paper will not be out by quark matter, I think we make the second point also preliminary, and then the paper will be coming out. So actually I have a paper draft, but it's in the, yeah, okay.
Okay, so since no more questions and comments, so let's close this discussion. We thank the two speakers again for the very interesting and presentation of the theory and experimental results on hypernuclei and nuclear production hadron collisions. Thank you so much. So I pass the